Hey, welcome back to part 6, and with that also the last part of our Kerberos deep dive series. This part will deal with the resource-based constraint delegation feature as the last form of the available delegation mechanisms in Kerberos. As with the other videos in this series, a quick note on the usage of Wireshark. We'll be using Wireshark to inspect Kerberos traffic throughout various labs in this video. And as Kerberos traffic is partially encrypted, the analysis of the packet details are a bit more difficult. So in this video series and in the labs, the Wireshark has been configured with the key material of all accounts within our infrastructure. So Wireshark will be able to decrypt the Kerberos traffic accordingly. Whenever you see a recording of Wireshark, whenever there's a blue background as depicted here, that means this data has been decrypted by Wireshark with the provided key material. If you want to learn more about this, you can go back to part 1 of our video series. Now let's get on with the basics of resource-based constraint delegation. As we have learned previously, there are 3 main forms of delegation in Windows Kerberos. We have the unconstrained delegation, where a service can simply perform the delegation against any other service within your infrastructure. We have the constrained delegation, where the targets of the delegation are restricted. So the impersonation can only occur against specific services. And then we have the resource-based constraint delegation that was added last. And this essentially works the same as the constraint delegation, but it reverses the way the delegation is defined. And in this part of the series, we are going to talk about the resource-based constraint delegation mode. The resource-based constraint delegation feature was added in Windows 2012, so the last form of delegation added by Microsoft. And what it does, it reverses the way the delegation configuration is defined. Until now, the unconstrained and the constrained delegation was always configured on the, let's say, front-end system that performs the delegation against another back-end system. And with resource-based constraint delegation, this trust is reversed, or the definition is reversed, and the delegation rights are granted by the backend system. So a backend system specifies which front-end system or systems are allowed to delegate to them. So if we look at a quick sample scenario, if we have our user, we have several front-end services and some back-end services. The back-end services are now the ones that define the delegation trust. So service X might only trust service A for delegation, and service Y might trust services B and C for delegation. Previously to that, so before resource-based constraint delegation, it was always the other way around. So service A had delegation rights configured for various backend services, and the same for B and C. And now the delegation rights are granted and configured on the backend resources. So when then a user connects to service A, this service, because it is trusted by service X, might delegate this user or the user rights towards this service, but not the other services. Now, why has this been introduced? What's the benefit of this? As mentioned before, the delegation privileges before resource-based constraint delegation were always granted to front-end services. So the back-end service, the one that is essentially actually affected by the delegation because it receives a delegated rights, or it's on the receiving end of the delegation, they had no control over who can actually delegate to them. So every front-end service that has delegation towards a backend system is potentially a security risk for the backend service, because again, it might impersonate any user, and that has in the end an effect on the backend system. And now, by reversing this the delegation principle, or the way it is configured, it's the backend service that has control over who can delegate to them and who is not allowed to perform delegation. Now, when you want to configure a resource-based constraint delegation, again, this is done on the respective domain object, but now on the backend service as mentioned. Still, that can be a user or a machine account. And what you require for this is only write permissions on that specific object. So compared to the previous forms of delegations of constrained and unconstrained delegation, where domain admin rights or equivalent were required, here it's only necessary to have write permission on the respective object. So for example, computer accounts within an Active Directory can configure resource-based constraint delegation on themselves, since they have write permissions on their own accounts. Whenever you configure resource-based constraint delegation, you only define which accounts, so front-end systems essentially, are allowed to delegate to you. You don't specify a list of allowed services anymore, as was the case with the constraint delegation. So it's only system A and B, but not HTTP or MS SQL or LDAP or whatever other services come to mind. The configuration has to be done via PowerShell. There's no built-in UI option in the administrative tools offered by Windows. And what you do is basically you get a list of accounts that are allowed to delegate to your specific service, and then you add this list to the attribute with the very nice sounding name of MSDS allowed to act on behalf of other identity. A quick example on this, what we want to achieve here is a delegation from FS1 to WS1. So FS1 should be able to delegate to WS1. That means the configuration has to be done the other way around. So WS1 has to allow delegation on FS1. So we configure the attribute on WS1. You can see I'm currently running a system shell on WS1. So we should have the required permissions to set this attribute on our own host. And what we first do, we get a list, or in this case, just one account that we would like to trust. So that this is the FS1 machine account. And then we specify this account in the attribute that was aforementioned on WS1. So we just use the set80 computer, or respectively set80 user commandlet, and if you want to configure that on a user, specify the principals allowed to delegate to account, attribute, and pass in the account that we just defined before that. And with that, the configuration is already done. You can see, as mentioned before, there are no services or other restrictions that you define. And if we just print out the property again on the machine, we should now see that indeed the FS1 account is allowed to delegate to WS1. So again, the configuration is applied on WS1, and we specify whoever else is allowed to delegate to us. Now, how does it work behind the scenes? The resource-based constraint delegation is essentially the same mechanism-wise as constraint delegation, especially in the protocol transition mode. That means the system that performs delegation is using S4U to self and S4U to proxy in combination to get a ticket in the name of a user to perform the impersonation. The only difference here is how the KDC actually validates the incoming S4U to proxy requests, or there are some other checks that are performed, but the mechanism to acquire the tickets are exactly the same as with constraint delegation. So just as a short recap, when we have a user, now the user is grayed out here a bit because it's not strictly required. The service that is allowed to perform the delegation, so the front-end service, can initiate the impersonation process on itself, as with we've already seen when we looked at the constraint delegation in protocol transition mode. But for normal operation, of course, usually there's a user connecting to the front-end service. So whenever then the service initiates the impersonation or the delegation, it will first acquire a service ticket on behalf of the user for itself with the S4U to self protocol extension, and then it will trade in this service ticket towards a ticket in name of the user for the target service in S4U to proxy. If you want to learn more about these mechanisms, the part about constraint delegation, specifically the constraint delegation in protocol transition mode, in part 5 of this video series contains more info about that. As I mentioned, there are a few more specific details on how the S4U to proxy request is validated by the KDC, and specifically if we look at the request that is sent, or any S4U to proxy request that is sent by default has the so-called resource-based constraint delegation flag set to true. So this is a default configuration if your systems are modern enough or up to date enough to know about the resource-based constraint delegation. And what this indicates is that the client that triggered this S4U to proxy request supports the resource-based constraint delegation mechanism, and the KDC should check accordingly if there's a configuration that would allow the S4U to proxy in this case. So the decision flow that happens on the KDC is as follows. If we have the situation that our front-end system Web1 initiates S4U to proxy to impersonate a user against the backend system DB1, the process looks as follows. So we start with the S4U to proxy request towards the KDC, and the first thing that the KDC verifies is whether there is a regular constraint delegation configured. So it will check whether Web1 is allowed to delegate towards DB1. So for constraint delegation, that will be a configuration on Web1, specifically this service allowed to send forwarded tickets to attribute. So this is what we've seen before in part 5. If constraint delegation would be configured for this case, the KDC would issue an according service ticket. Now, if this is not the case, so if constraint delegation is not allowed for Web1 to DB1, either it's another system or it's not configured at all, the decision flow continues, and the KDC will check if this aforementioned resource-based constraint delegation bit or flag is set in the request. And this, as I mentioned, is usually the case. So if this would not be, the process will be aborted with the bad option error. If this is the case, however, the decision flow continues, and the KDC will then evaluate resource-based constraint delegation. So it will now check the receiving system of the delegation, so the backend system, since resource-based constraint delegation is configured on the backend and not on the front end. So it will check whether or not Web1 is listed in this service allowed to receive forwarded tickets from attribute of DB1 of our backend system. And if this is the case, then the service ticket is issued again. So as here we would end up if we are dealing with constraint delegation, and here we end up if we are dealing with resource-based constraint delegation. And of course, in the error case, it would again stop the flow with the bad option error. Now, from an attacker's perspective, attacking resource-based constraint delegation is not much different or essentially the same as with constraint delegation. What you need to keep in mind that for resource-based constraint delegation, there is no distinction between the two modes that we've seen with constraint delegation. So there's no Kerberos only or protocol transition. The behavior for RBCD is always identical to protocol transition. That means, as we've already learned in part 5, there needs to be no user presence or specific form of authentication to occur before the delegation process can be started, because again, the service is allowed to get a ticket that basically represents the user presence itself via S4U to self, and then use that ticket within S4U to proxy. So as a result, again, if you enable a resource-based constraint delegation, the delegating service can again impersonate any user it wants. It doesn't need any user interaction to happen before that. So this is just something to keep in mind. So for the attacker, again, that means we need, of course, control over the account that is enabled for resource-based constraint delegation. So the front-end account that will perform the delegation. And then we must know the principal name of the account that we want to impersonate. And with that, we can then abuse the resource-based constraint delegation rights that are granted to impersonate any user against the allowed targets. And since, as we've learned before, we don't specify any target services in resource-based constraint delegation, only allowed accounts, the delegation works against any service on the allowed target. So that could be HTTP or LDAP or MS SQL or whatever else is operated on the account. Let's look at a quick example on how this can be used. First, we check the current setup. So we have a service account, and you can see on the service account itself that it represents the front end. There is no configuration regarding delegation. However, on the backend system, if we check it with PowerShell, we can see that the aforementioned service account is indeed allowed to perform delegation, resource-based constraint delegation against CA1. So if we are in possession of this account's credential, we can then impersonate any user we want against CA1. For the attack itself, we switch to our Windows client, and we are going to use Rubius to request and perform the necessary tickets of the operation. Currently, you can see we have no tickets in our logon session, and subsequently, we are also not able to access any resources on CA1 or any protected resources. Now, as a first step, we need, as with the other abuse scenarios, we need a TGT to actually authenticate ourselves as the service account. For this, we just pass along the credentials or the key material. Maybe we found that on a share somewhere, and with that, get a ticket granting ticket in the name of the account SVC IAS that is allowed to perform delegation. So you can see in Wireshark, this is just plain ASREC and ASREP. Now with the TGT, we can then exploit basically the rights given to us. So we can use the s4u command in Rubius. We specify the user that we want to impersonate and the target service. So the target service has to be on the machine where we allowed to delegate to. Again, any service is valid. Just taking CIFS as an example. We pass the ticket directly into our session and we specify the ticket granting ticket. With this, we can see apparently everything worked as expected. So Rubius will perform s4u to self first and request a service ticket in the name of lab admin to its own account. And with that ticket, which can be used as a proof in s4u to proxy, s4u to proxy is then used to acquire a service ticket in the name of lab admin towards the target service where we want to impersonate the user. So in Wireshark, we can see those two steps as well. We have the s4u to self request and reply. In the s4u to self reply, we see that we get a ticket in the name of lab admin issued towards SVC IAS. And the cipher 5D6C is then again repeated in the s4u to proxy request in the additional ticket section, FD 5D6C, as you can see. And as a response, we then get the actual ticket for CIFS in CA1 with the cipher 08FB. And if we actually now try to access the share with our ticket, so we can see we have now a ticket for CIFS on CA1. Let's just repeat the previous command. You can see that now works. So we have access to protected resources on CA1. And let's take again note of the cipher of this ticket, so 08FB4. And in the session setup request of SMB, we can find again the same ticket present here, which means this is the ticket that was used to access the share. Now, one more thing on a specific benefit of resource-based constraint delegation to attackers is that it can also be used or chained together with constraint delegation to abuse a specific case in constraint delegation that we've talked about previously in part 5 of this video series. As we've learned in constraint delegation, we have two modes available, either Kerberos only or protocol transition. And if we operate constraint delegation in Kerberos only mode, we need a user's service ticket to perform S4U2 proxy. S4U2 proxy requires a proof of the user's presence, and this comes in form of the user service ticket. This ticket is obtained when the user initially connects to the delegation service via Kerberos. So the user passes along their ticket, and the service then uses that ticket in S4U2 proxy. We've also already learned that this specific ticket must be flagged as forwardable, otherwise it is not viable as proof. That means our user must not be marked as sensitive, the user is not a member of the protected users group, and also it's not possible to use a ticket acquired via S4U2 self, unless of course protocol transition is enabled. But since we are looking at Kerberos only mode, a ticket from S4U2 self will result in being not forwardable. So as a consequence of all of this, that means that we can only abuse Kerberos constraint delegation in Kerberos only mode when there's actually a user there. So we need somebody to connect to our system in order to abuse and delegate their permissions to another system. Now, this of course is quite a constraint when it comes to the attacker's perspective, but as we will be seeing in the next few slides, it's actually not that restrictive, because in certain cases we can use resource-based constraint delegation and chain it to constraint delegation to get our hands on a ticket that is viable for S4U2 proxy. For this, we'll look at a high-level overview on how the attacker setup looks like. So first, we can see we have the KDC, we have services that are under control of the attacker. Now, specifically, we need two instances, and we have the backend system, db.local. Now, and then there's a delegation relationship between those two. So web.local is configured for constraint delegation with Kerberos only towards db.local. We as an attacker would not like to abuse this specific relation between those systems and impersonate any user that we want against db.local. Now, before we look into RBCD, how RBCD could be abused for this, that would mean that we need an actual user to connect to web.local. So we have that user service ticket and can then use that service ticket in S4U2 proxy to get a delegation ticket towards db.local. As you can see now on this diagram, there's no user present, so there's obviously a different solution for this, and that's where resource-based constraint delegation comes into play. The first thing that the attacker has to do is to enable resource-based constraint delegation. Specifically, the attacker will configure, since he has full control over those two instances, he will configure RBCD on web.local and enable foo.local as a delegation system. So foo.local will then be allowed to delegate to web.local via RBCD. Again, remember, we can configure that on web.local because the configuration of RBCD only needs write permissions on that respective object. Now, with that in place, we can start the abuse flow. Since the attacker also controls foo.local, so any other system within the domain, we can then from that system start to perform the impersonation flow. And this all starts with requesting a ticket in the name of the user that we want to impersonate. So admin, for example, with S4U2 self for our own account. So S4U2 self always is meant for a ticket for our own account, and this works without any problem. So the KDC, of course, will validate whether we are allowed to do that, which is no problem in this case. And we will get back a service ticket for admin. Now, with this service ticket, we can then trigger the next step and request a ticket for admin to web, so to this system over here. Now again, remember, we are allowed, or foo is allowed to delegate to web.local because of this configuration of RBCD. So whenever this request is handled by the KDC, it will again check if we are allowed to do so, or if foo is allowed to do so. And since we have previously set up this configuration here, this will also be a valid request, and the resulting ticket can then be used, or is a valid impersonation ticket for admin on web.local. Now this part, this flow that we've just talked about, is essentially resource-based constraint delegation. It's exactly what we've seen before in the abuse scenario. It's S for you to self and S for you to proxy chain together, and with that, or the result of that, is a impersonation ticket in the name of admin in our case for the target system web.local. And again, this is allowed because we just configured this RBCD permissions ourselves. Now, with this ticket, we can then basically forward it or transmit it to web.local as if we would, if we actually access the system over here. And it's important now to know that this ticket that results from a valid RBCD protocol exchange is indeed forwardable. So it is a forwardable ticket in the name of admin towards our web.local system. And now this means that we have now fulfilled the prerequisites for the constraint delegation with Kerberos only mode. So we have, via RBCD, essentially faked a user's presence and created a forwardable ticket that can now be used in S4U to proxy to abuse this part of the delegation setup. So that's exactly what happens next. The web.local system will trigger S4U to proxy. It will forward or attach this service ticket of admin. The KDC will again verify everything is in order. So is the ticket valid and forwardable? Is the user, of course, not protected or sensitive? And if the delegation rights allow this request. So is web.local allowed to delegate to db.local, which was already the existing setup. Again, if everything is valid, we will receive a service ticket for admin on db1, and this part then concludes the constraint delegation feature, and we will, as a result, be able to connect as admin towards the db.local system. Now, we will be looking at two different attack setups in our lab environment. The first setup is essentially exactly what we've seen on the slide before. We as an attacker control two systems, in our case specifically systems FS1 and WS1. There's already a constraint delegation in Kerberos only mode configured. We have the system WS1 that is allowed to delegate towards CA1. Again, in Kerberos only mode, that means we somehow need a user's presence or a user's forwardable service ticket to exploit this constraint delegation. What we want to do is we want to impersonate the user lab admin towards this, this backend system CA1. Now, how do we approach this? As an attacker, we've learned the first step is to configure a resource-based constraint delegation between the two systems that we control. So we, since the RBCD is configured on the recipient system or the receiving system, backend system of the delegation, we configure that on WS1 and allow the front-end system FS1 to delegate to us. Then on FS1, we start the impersonation flow, so the resource-based constraint delegation, to acquire a ticket in the name of lab admin towards our WS1 system. And again, WS1 is the system that is configured for constraint delegation. And once we get this ticket, we can then pass it along to WS1 and use it to just simply trigger S4U2 proxy and abuse the already configured constraint delegation to get an impersonation ticket towards CA1 in the name of labadmin. Quickly visualized, the setup will then look like this. So we have in the middle WS1. This is the system that is allowed to do or to perform constraint delegation in Kerberos only mode towards CA1, the backend service. And on the other end, we have FS1, which is the resource that we as an attacker control as well. And we configure resource-based constraint delegation. So FS1 will be allowed to delegate to WS1 and WS1 will be allowed to delegate to CA1. So let's jump in the lab. Just as the initial situation, we have on both our systems FS1 and WS1 a system shell running just to simulate an attacker having full control over those systems. And then on WS1, we first want to configure the resource-based constraint delegation between FS1 and WS1. So since FS1 should be able to delegate to WS1, we need to define it on WS1. First, we're going to grab the account that should be allowed for delegation, which is the machine account, FS1. And with that, we then are specifying this the respective property via the set80 computer commandlet on WS1 and pass along the account that we just defined previously. And this should then enable the resource-based constraint delegation. Let's quickly verify if this worked. We'll query the principals allowed to delegate to account property on WS1, and we should see that FS1 is indeed now allowed to delegate towards WS1. So this is the first step of our setup. And from that, we can then jump onto FS1 to start the process, the impersonation process. Now, as we before, we'll run Wireshark in the background to record everything. And the first thing that we need to do is, as with almost all demos, now we need a valid TGT for our account, for the machine account. We'll be using the TGT Delectric with Rubius to get a usable TGT in base64 encoded format. Next, the actual impersonation in the resource-based constraint delegation can be done with the S4U command. We specify the target user account, so that will be labadmin in our case, and any valid SPN on WS1. Again, it's resource-based constraint delegation, so which doesn't really matter. We're using CIFS, and then we provide our TGT. Let's look at what Rubius did. First, we have the S4U2 self request. So we get a ticket on FS1 in the name of a labadmin, so a ticket to ourselves. And with this ticket, we then call S4U2 proxy and ask for a ticket on CIFS WS1, so the target system, again in the name of labadmin. If we look at Wireshark, we can see the same things. So we have the S4U2 self request, where we ask for a ticket in the name of a labadmin to our own account. So WS1, and as a result, we then get the corresponding ticket. So nothing surprising or new here. The ticket is forwardable, so again, it can be used in the next step in the S4U2 proxy, and this will then be the following request. In S4U2 proxy, we specify that we would like to have a ticket for CIFS on WS1 now. And we pass along the additional ticket that we just come from the S4U2 self step. So with this, again, the ticket is forwardable as we've seen before in the name of labadmin, so everything should work. And indeed, we get back a ticket that can now be used to impersonate labadmin on WS1. This resulting ticket, again, because we are configured for resource-based constraint delegation, is also forwardable. So that means we can then use it in the next step of the abuse. So what we can do now is we take this ticket and we move over to WS1. because from there we can then continue the abuse of the constrained delegation part. So let's quickly take note, store the ticket for later, and as before, we again start with fetching a TGT for the machine account of WS1, so we can then authenticate the following requests, again using the TGT deleg command of Rubius, and now we have the TGT available. Next, also to abuse the S4U to proxy step, we can again use the Rubius command with S4U, specify the allowed target service on CA1, and pass in both the respective tickets. So first we pass in our TGT to authenticate the request, and then we pass the additional ticket, and now we take this ticket that we acquired with a resource-based constraint delegation. Let's clear Wireshark so we have a fresh trace of what happens if we issue this request. We can see that Rubius only performs one step, the S4U to proxy, in the name of lab admin towards the target service that we specified, so CIFS on CA1. And this apparently seems to have worked. Everything is in order, and now we got a ticket. Now we can use it. Since we've loaded it into our session, we can see we now have a ticket in the name of lab admin towards CIFS on CA1. With this, we can also now try to access the resources C drive, for example, over SMB, and as you can see, this works. So we are indeed authenticated. And if we look at Wireshark, we see one request in Kerberos. This is S4U to proxy. And if we again look at the details, we can see that we ask for a ticket towards CIFS on CA1, so the target service, and we pass along the ticket that we previously got via the resource-based constraint delegation trick. And the ticket is, of course, issued to lab admin. So the resulting ticket will also be for lab admin on CIFS1. If we quickly check the cipher here, 8F8, this is the ticket that we pass along as an additional ticket, and this is the same that we got via the S4U to self and S4U to proxy trick on FS1. As a result of all of this, we get back a ticket from the KDC issued to lab admin with 7BE6, and in the following SMB setup request to access the C drive on CA1, we can see that we pass along the same ticket as well in the authentication layer 7BE6E. Now let's look at a second abuse or attack scenario that starts a bit differently. We as an attacker have control over one specific account, in our case SVC IAS. That means we might have the credentials available for this account or the Kerberos key material, something like that. And this specific account is again configured for constraint delegation to our target backend system CA1 using Kerberos only mode. So that means technically we would require a user's presence to abuse this delegation rights. What we would like to achieve is eventually to impersonate a user lab admin towards this backend system CA1. And now the difference to scenario 1 is that we currently don't have another system available or another account, but in the default configuration of a new domain, regular users can add up to 10 computer accounts to the domain themselves. So we can take advantage of that and add our own computer account to the domain and then subsequently use this additional computer account for the resource-based constraint delegation trick. So the approach is as follows. First, we add our own computer account to the domain. Then we again specify or configure resource-based constraint delegation on the account that we already control, so the SVC IAS, to allow delegation via RBCD from the computer account that we just added. Then we, from the computer account, from this new attacker computer account, we initiate the resource-based constraint delegation mechanism to request a ticket in the name of lab admin for our service account. And once we have that ticket, we can then use it from the service account as proof in the S4U2 proxy, so to abuse the constraint delegation that is configured to eventually get a delegation ticket to CA1. For this attack scenario, we're going to use some Linux tooling. Specifically, we are back on our Kali machine. First, quickly, let's verify the current configuration in our domain. First, the SPN associated with the SVC IIS account. We can see that we indeed have one set. So this is HTTP on WS1. So this SPN is associated with our service account SVC IIS that we have control over. And if we check the current resource-based constraint delegation, there's nothing configured on this account. However, the constraint delegation, if we check the Active Directory object, we can see that SVC IIS is configured for constraint delegation with Kerberos only towards the CIFS service on CA1. So that's our target that we eventually want to attack. Now, as a first step, we will add a new computer account to the domain. For this, we use the in-packet add computer tool. We specify the name here ATK. The dollar denotes the machine account type. Then we can provide our own password. Let's take password 123. We're going to use that later. And then the IP of the domain controller that we want to interact with. And lastly, credentials of a valid domain user. Here we specify the credentials of the service account that we have compromised. So we know that the password, maybe we found it somewhere on a file share or similar. So apparently this worked. So we have now a new machine account joined to the domain, and we can check that on the domain controller itself. We should find that within the computers OU, a new machine called ATK was created. Good. Now with that in place, next we can use the in-packet RBCD tool to add the resource-based constraint delegation config. Specifically, what we want to is that the account ATK is able to delegate to SVC IIS, so the service account. So we specify this along with the DCIP and the credentials of the account where we want to change the configuration. So again, this will be the SVC IIS account, since resource-based constraint delegation is configured on the receiving or the recipient account, which is SVC IIS. So let's see if this works. I think in here we might have a typo in the IP address, and indeed there's a timeout, so let's quickly remediate this. There was a 1 missing, and now this should work as well, and we should end up with the changes being applied. Again, so now as a result of this, SVC IIS has configured RBCD and allowed ATK, the machine account, to delegate to it. We can see that on the domain controller again, just repeat the previously issued command to query the principals allowed to delegate to account, and we can see indeed ATK is now in this list of principals that are allowed to delegate to us. Good. So with that, we can now start the actual abuse. The first step is the resource-based constraint delegation part. So we use the get SD command of in-packet to request a service ticket. We request it as ATK, and we want to impersonate against the SVC IIS. So we specify the associated SPN, which user we want to impersonate, in our case lab admin, and then the DC IP address, since we're not domain joined. And now, since we want to act as ATK, because ATK is allowed for resource-based constraint delegation, we need to pass along the credentials of the ATK account, so the computer account that we previously added to the domain. With this, we should now see 3 things. First, in-packet will fetch a TGT, then perform S4U2 self, and subsequently S4U2 proxy, which will result then in a ticket. In Wireshark, we see the same thing. We have an ASREC failed with pre-auth required, repetition of ASREC, and then a reply, so the TGT. Now you might notice here we have yellow background in Wireshark. This means that Wireshark was not able to decrypt the traffic. The reason for this is because the ATK account which is created is not yet in the key tab file that we provided to Wireshark, so that means there's some key material missing. Now you might see some messages that are part blue and part yellow because some things can still be decrypted because the key material is in the key tab file. For example, for this S4U2Self request and response, some parts are encrypted with key material that we have, so we can look at that. So what we see here, we request a ticket towards ATK in the name of the impersonated user labadmin. So this is S4U2Self. And in the response, again, some parts are not entirely decryptable because we're missing the key material, but still we can see that we get a ticket back as a result of S4U2Self. The ticket is for ATK, and in the part that we still can decrypt, the flags are also present, so we see that this ticket is indeed forwardable, so it can be used in S4U2 proxy. Then the next step is S4U2 proxy, where we ask for a ticket for HTTP on WS1. We pass along this ticket that we just got before. So let's quickly compare. The ticket that we got before, the cipher starts with 5BAD, and we should see the same thing in the additional ticket section, indeed 5BAD. As a result then of the S4U2 proxy, since we have configured the according delegation rights, we now get a ticket for HTTP on WS1, which should be issued to our user that we want to impersonate, namely the lab admin. If we look at the correct part of the return ticket, we should find that here. And as well, ticket is forwardable, so it means we can then use it in the next step of our attack. So with this ticket, we now have concluded the first part of the attack, and we can use this ticket to abuse the already configured constraint delegation. Because this is a forwardable ticket, it essentially represents a user's consent or authentication towards our system, and with that we can then use that as a proof in S4U2 proxy. So we again use the get st tool of InPacket, specify the target. Now this is CIFS on CA1, and this has to be aligned with the allowed delegation rights for SVC IAS. So if we check that again, just quickly on the domain controller, we can see CIFS on CA1 is indeed allowed. So here we can then tell or configure the user labadmin that we want to impersonate, and we pass along this additional ticket just by file name that will be used as a proof in S4U2 proxy. The DCIP address as before, and then the credentials of the account that now performs the impersonation or delegation, which is SVC IAS. Let's check if all of this works. So it should pick up the ticket directly from the disk, no need to specify it on the command line. And again, we see that it will fetch a TGT to authenticate the next request, and then S4U2 proxy will be issued, and the ticket is saved to disk as well. In Wireshark, same as before, ASREC, ASREP with pre-auth required, ASREC and rep repetition. Now we can decrypt everything since we already have the key material. And then the S4U2 proxy request, where we get a ticket for the CIFS on CA1, so the actual target that we want to attack. And we provide the additional ticket that we got previously, which is issued to labadmin. So the result should now be a ticket in the name of labadmin towards CIFS on CA1. And we should find that in the reply to our S4U2 proxy request. Since everything here is forwardable, let's check the flag again. This should not be a problem. And indeed, we get back a ticket for CIFS on CA1 in the name of lab admin. Now this ticket as mentioned, has been written to disk as well. So to use that with the in-packet tooling, what you can do is set an environment variable called Kerberos CC name and specify the path to the ticket, and this will then be picked up by the in-packet tools to authenticate. For this, you simply specify the -k command, optionally also the no pass, so you're not prompted for an additional password since we already have authentication material, and then of course the account that we want to use. So this is the lab admin, since the ticket was issued to lab admin. And then with that, we select the target system, CA1. We are going to use the PSExec tool of in-packet, so this will authenticate over SMB or CIFS. Specify the target IP address of the system, since we don't have the we can't look it up since we're not part of the domain, and then that should already be good to go. And indeed, this worked. We can see that we now have system level access on CA1. So indeed, we were able to impersonate the lab admin. As a last thing, let's verify the session setup request of SMB within the Kerberos authentication layer. We should now find that we have indeed authenticated using a Kerberos ticket, and the ticket is the one that we previously requested for lab admin, and that concludes our attack. Let's quickly summarize what we have seen now in those two demo setups. So to abuse constraint delegation with RBCD, we see that we can use, or we have learned that we can use the resource-based constraint delegation to acquire a ticket, a forwardable ticket, as any user. This is intentional by design within RBCD. However, we can then also use this ticket in the S4U to proxy exchange in another constraint delegation setup. For an attacker, this means that, or to be able to abuse this, we as an attacker must first have control over the actual account or system that is configured for constraint delegation. And then we also need an additional account or a system where we can subsequently configure the resource-based constraint delegation. So we can chain those two delegation mechanisms together as seen before in the demos. Now, there are some additional requirements for this account. Specifically, this additional account must have an SPN assigned. The reason for that is that the resource-based constraint delegation mechanism will not work on an account that doesn't have an SPN. Since in resource-based constraint delegation, we issue an S4U to self request. So we request a ticket for ourselves, and this only works if there is an SPN available. Now, with that said, there are different options where we could acquire such accounts or potential candidates that we can use. The easiest, I would say, is simply a machine account. We've seen that in both demos, either a pre-existing one or a one we add ourselves. And the reason for that is that all machine accounts in an Active Directory have SPNs assigned by default, so implicit SPNs like the host SPN, for example. So there's no need to add an additional one. Another option would be that the attacker controls a service account, so a user account that is used as a service, which already has an SPN assigned. This would work as well. And lastly, it could also be that we have any arbitrary accounts and the according privileges to add an SPN to this account. So this would then also make it eligible for this attack scenario. However, the chances of that are less likely, since in general, to configure SPNs within an Active Directory environment, you need domain admin privileges. So for that to happen, there must be some other misconfiguration, or you already must have control over an account that has high enough privileges to essentially compromise the domain. Now that we've seen how resource-based constraint delegation can be abused either on its own or in combination with constraint delegation, let's also quickly summarize what's there to consider and recommendations you should think about when dealing with this mechanism in your own infrastructure. What we have seen so far is that resource-based constraint delegation is technically equivalent to constraint delegation under the hood, constraint delegation in protocol transition specifically. So the working mechanism is the same. It uses S4U to self and S4U to proxy. However, RBCD requires less privileges to be configured than the other forms of delegation, where for unconstrained and constrained delegation, you need domain admin privileges or the respective SE-enabled delegation privilege. For resource-based constraint delegation, you specifically need to have write permission of a given object. So anyone that joins a computer to the domain or is local admin on a computer can configure that on the respective computer. So you might have much more occurrences of RBCD actually being configured by various users in your environment. The impact of abuse is, again, as with constraint delegation, limited to whatever the defined target systems are. So keep that in mind as well. If you employ resource-based constraint delegation, consider the following points. As with the other forms of delegation, the configuration should be as restrictive as possible, meaning delegation should only be configured on a system where it is actually required, and the respective privileges of the individual systems should be kept in mind. So a low privileged, maybe highly exposed system like a web server having delegation privileges against a high privilege system like a domain controller doesn't make much sense security-wise. Furthermore, the systems and accounts that are involved in the delegation configuration should again be as protected as strongly as possible. Hardening measures should be applied accordingly. And the users within your Active Directory environment, especially the high privileged accounts, should be protected by either adding them to the protected users group or marking them as sensitive, so the delegation mechanism does not work for them. And along with that also goes the least privilege principle, so generally reducing the permissions of your accounts in the event of a compromise by an attacker. The impact is less, or you can lessen the impact of that scenario. And then lastly, also consider implementing monitoring measures, specifically in the context of RBCD for your high value accounts, for any system that has delegation rights configured, and for specifically RBCD related configuration, because it's much more likely that this will occur, since it requires less privileges than the other forms of delegation. In the end, a few more details regarding the monitoring for RBCD abuse. So events that you could consider to monitor specifically to detect RBC abuse. On the one side, we have the modification or the addition of new resource-based constraint delegation rights. We've seen that this is a specific property that is changed on a domain object. So the event 5135 that fires when a directory service object was modified will reflect that as well. Specifically, you'll have to look for the change to the MSDS allowed to act on behalf of other identity attribute. Now, interesting to see is that whether you change it by a PowerShell or you use a tool like Impacket, as we've done in the demos before, the value displayed here as the new value of the attribute is always a malformed security descriptor. So you will have to dig more into the log files or into the configuration to actually retrieve the current value of this attribute. But at least you get informed about the attribute being changed. And then secondly, we've also seen the exploit with adding a new computer account to the domain. So RBCD can configure from that account. So you can also look for the creation of new computer objects. That will be ID 4741. And again, here look for the new computer account that was created, also by which account it was created. Is it in line with all the other similar events in your environment, and so on and so forth. With this, we have reached the end of both this part and as well the overall video series on Kerberos deep dives. I hope you enjoy it. If you have any questions or remarks, please leave a comment and we'll make sure to follow up on that. Thank you very much for watching.